Hello and welcome everybody. It's 5 minutes after the hour, so it's about time to resume our lectures on string theory. Today I will briefly review a few things that we did in the last lecture, and then I'll try to finish with part 2, which is our basic introduction to relativistic strings. I have already posted the first example sheet with 4 problems that you should all attempt. 2 of the problems should already make sense now, and the other 2 after finishing these lectures. For these example sheets, I will then provide you with worked solutions, which I will post in about 2 weeks. So in between, I would like to encourage you to have at least a go at these problems on the example sheet, and hopefully a few more as suggested as we go. So let us briefly review from the point where we introduced the Polyakov action, which is one of the ways to define a classical string theory. In the setup with the Polyakov action, we work in a setup where we equip the worldsheet with its own intrinsic metric, which is independent of the metrics that we have on Minkowski spacetime. And then there is a natural action principle for such a map between 2 Riemannian, or since we admit indefinite signature pseudo-Riemannian manifolds, that's strings with the Polyakov action. And generally, this is what physicists call a sigma model, and mathematicians an energy functional for such a map, and it is given by formula 28. So what we then discussed last time is that it's invariant under reparametrizations and also under Weil transformations, which are transformations where we multiply the metric by a positive function. We then worked out the equations of motion. We discussed that the worldsheet, the intrinsic worldsheet metric, is an auxiliary variable which we can eliminate, and then we get back the number Goto action. So these 2 theories are classically completely equivalent. The Polyakov action has the advantage that we can switch the perspective and read it as an action for a 2-dimensional field theory, where we have scalar fields living on our worldsheet manifold sigma, who just happen to have a target space which is d-dimensional Minkowski space. In this context, we looked at the energy momentum tensor of this 2-dimensional field theory, which is worked out in equation 37. And the vanishing of, or the equation of motion for the auxiliary field worldsheet metric then becomes a condition that the energy momentum tensor vanishes. This is a constraint, as we stressed, that is imposed on top of the equations of motion, and I think today we will understand completely how we can do this. An additional useful thing to look at is energy momentum conservation equation, which on a curved worldsheet means that the energy momentum tensor is covariantly conserved. And that is something from which we also will draw important consequences later in this lecture. Now, we stress the particular role of Weil transformations, which sets the Polyakov action in 2 dimensions apart from any other dimension. So if we can write down Polyakov-like actions for point particles or membranes or higher dimensional objects, but they don't have this additional invariance under Weil transformations, which, as we will see, provides us with a link to what is called conformal field theory. The conformal gauge, also very important. The worldsheet metric has 3 independent components, and we have 3 independent local symmetries. And this allows us to impose a very convenient gauge condition. It's generally true that any 2-dimensional metric is conformally flat, so we can write it as a flat metric times a positive function. But with the additional Weil transformation, we can even remove the so-called conformal factor and impose that we have a flat metric on our worksheet. This holds at least locally, so it means around each point we can choose coordinates such as the metric is a standard flat metric. But this will be enough for our purposes. The conformal gauge is not a complete gauge fixing because there are coordinate transformations which just multiply the metric by a positive function. And this positive function can then be removed by a compensatory Y transformation. And therefore, our reparametrizations are not quite fixed. The remaining transformations we will refer to as conformal transformations. And they are the reason why, when we do string theory with a Polyakov action in the conformal gauge, we are within the realm of conformal field theory. It's hard to overemphasize the importance of this, and in particular, the next two parts of these lectures will draw on this observation that we are working with the conformal field theory. But for the time being, let us look how Polyakov strings look in the conformal gauge. So this slide is more or less for reference. Let's briefly go through it. The metric is a flat Minkowski metric. The equation of motion now becomes the two-dimensional wave equation, which we know how to solve in general by left and right moving modes. But we will also have to impose boundary conditions, which we will see today how this works, and we have to impose the constraints. And there is only taking into account that the tracelessness of the energy momentum tensor already holds without using the equations of motion. We have only two remaining independent conditions that we have to impose. And we will see today how we can do this in practice. Okay, that was a side remark. Now let's go to the topic of Litecoin coordinates. So the structure that we see is with a two-dimensional wave equation and its general solution suggests that it is sometimes useful to use Litecoin coordinates or null coordinates, which are these linear combinations of the worldsheet time and worldsheet space. So if you draw a picture, if sigma 0 is our time direction and sigma 1 is our space direction, we now take coordinates which run along the light cone, and that often leads to important simplifications. But first, let's see how we can rewrite everything in terms of Litecoin coordinates. My notation convention is that the Litecoin indices take values plus and minus, and I use letters like A, B, C to distinguish them from standard worldsheet coordinates where alpha runs from 0 to 1, and where one coordinate is time-like and the other is space-like. General rule for converting tensors is that you have to use the Jacobian of the coordinate transformation, which I've given you here in Formula 51 for reference, and then you can convert lower and upper indices between the two types of coordinate systems. In particular, we have now Litecoin derivatives, which are linear combinations of d0 and d1. And we also have Litecoin differentials. And if we rewrite the metric, the standard Minkowski metric in Litecoin coordinates, then it takes this form, which is off diagonal. And here the zeros indicate indeed that the coordinate directions are along the null or Litecoin directions of our metrics. That's why the metric becomes off diagonal if you write it in these coordinates. Good. Now, one immediate advantage we see if we now write the wave equation in Litecoin coordinates, it just becomes d plus d minus on x equals to 0. And in this form, it's obvious that the solution takes the form arbitrary function of sigma plus arbitrary function of sigma minus. Energy momentum tensor, there we have the tracelessness condition. In Litecoin coordinates, this becomes the vanishing of the mixed components. So the constraints are that the so-called pure components, t plus plus and t minus minus, have to vanish. And we can also rewrite energy momentum conservation, like so. And then we see t plus plus is independent of sigma minus, or t plus plus is just a function of sigma plus, t minus minus is just a function of sigma minus. So as far as the propagation of stress energy on the worldsheet is concerned, the so-called left and right moving parts of the motion of the string are completely decoupled. And that's a very important property, because it tells us that our two-dimensional problem on the worldsheet decouples often into two one-dimensional problems in the Litecoin coordinates. Good. Let us then ask, what are the conserved quantities that we have in our theory, or conserved charges? There's a general theorem, the Noether theorem, which states that with every symmetry you have a conserved current. That means, yeah, that something that you have a vector field called a current, which has this conservation equation, or actually, if you do it on a curved worldsheet, then I should write this as, as a covariant conservation equation. But of course, in the conformal gauge, this becomes something that we can write with partial derivatives, because the worldsheet metric is flat. And in fact, if you write it out, then such a conservation equation in Litecoin coordinate takes this form here. Okay, and this would be for conserved currents on the worldsheet. And this will be helpful if we consider the invariance under conformal transformations that we have in the Litecoin gauge, and then show that this leads to infinitely many conserved charges, which we can label by integers and parameterize in a certain way. I will go over this over much detail immediately now. And then we also have symmetries in space-time, Poincary transformations, and the associated conserved charges are the total momentum and the total angular momentum of the string. We will also briefly go over this. So let's talk about conserved charges related to conformal symmetry. The key point here is that t++ is only a function of sigma minus, and we will now, for definiteness, consider on the plus sector and ignore the minus sector. Now we are doing, obviously, since we have both sectors, we are doing, or for concreteness, we take closed strings. I will briefly state the results for open strings later on. That means we have periodic boundary conditions here. Now, the way I can get infinitely many conserved quantities is to observe the following. That I can take any function f sigma plus, which is smooth and satisfies my boundary conditions, and multiply it with t++, and I still get something which is conserved in the sense that it is independent of sigma minus, and therefore d minus of it vanishes. What we have here is called a conserved chiral current. We have seen on the page before how the current conservation equation on the worldsheet looks like, but due to this decoupling, we can have more special chiral conserved currents where these terms here vanish individually rather than just as a sum. So we have a conservation equation in each so-called chiral sector. If I have a conserved current, then the way I get the associated conserved charges is I need to integrate over space, which in our case means we integrate over the worldsheet coordinate sigma 1. And this is then formula 64, where for any function f, I write down the corresponding conserved quantity. I take the conserved current and integrate it along the string. Good. Since we have not discussed the Noether theorem in general, we should check that this is really conserved, which I leave for you to do in detail. Conservation means independence of worldsheet time sigma 0. And what you then have to do is you take the sigma 0 derivative, you pull it under the integral, you use your conservation equation, and you will also need to use the boundary conditions. And then you should see that this vanishes, and therefore LF is independent of worldsheet time. Now, to organize or to parameterize these conserved quantities in a non-redundant way, we use that every periodic function can be expanded in a Fourier series. and the exponentials then form a basis of functions in which all periodic functions can be expanded, labeled by an integer m. And this allows us in formula 266 to write down an infinite set of independent conserved charges by just making special choices for the function f. By the way, you will see here that the basis function depends on sigma plus, while I have written a sigma 1 here. But if you have understood what conservation means, it should be clear why I can evaluate this with sigma 1. Good, so this gives me one infinite set of conserved charges for t++. For the closed string, the same happens for t minus minus, and then I have a second set. Now, that means also that our constraints, which are the vanishing of the pure components of the Litecoin energy momentum tensors, become the 2 times infinitely many conditions Lm equals Lm tilde equals to 0. But this is now, we now have a great insight because we have just shown that these quantities are conserved. So they are independent of worldsheet time. And that means if I impose the conditions equation 68 at 1 worldsheet times, they will automatically hold for all worldsheet times. And that means that I can impose the constraints as initial conditions. That really makes our life simpler or very easy. It shows that our constraints are what is called first-class constraints, which are consistent with the time evolution of the system. If you don't have this kind of compatibility, if you have a second-class constraints, then the theory of constraint systems becomes much more complicated. But lucky us, we don't need to go into this today. And we now have at least a complete understanding what classical strings are. Their physical configurations are described by solutions of the wave equation, which satisfy certain initial conditions and certain boundary conditions. And that, in a sense, completely characterizes what we are dealing with. We will see though, that the quantum theory is much more interesting and much more challenging in a sense. So I did this for definiteness for closed string. For open strings, you can repeat the analysis. But here the boundary conditions couple left and right moving modes. Yeah, you will see later explicitly from the explicit solution that what happens if that left moving wave runs into the boundary, is reflected and goes back. So left and right moving waves combine into standing waves. But you can still construct conserved charges by combining contributions from left and right movers, or from t plus and t minus, and the resulting expression is given here in formula 69. And I leave it to you to derive this formula, and I give also a hint how by a certain trick you can again reformulate it as a problem with periodic boundary conditions. Okay. Good, so that was conserved charges for conformal symmetry. Now let's also briefly talk about Poincary symmetry. We have again brought back for us the Poincary transformations. Now, if you are familiar with the Noether theorem, or a convenient shortcut is the so-called Noether trick. So if you're either familiar with this or invest the time for look it up, you can do the derivation. But for the purpose of the lectures, I just state for you what the conserved currents are. They're given in formula 71. Now, if you don't do the big exercise of deriving these, then you should at least do the smaller exercise by really verifying that these currents are conserved. And as usual, for conserved currents associated with symmetries, you will find that you need to use the equations of motion. So these are on-shell conserved currents. And by the way, for those who are not familiar with covariant derivatives, you can do it with partial derivatives, which corresponds to doing the same exercise in the conformal gauge rather than in a general coordinate system. Now, main thing is that you convince yourself that these are conserved currents and that you must use the equation of motion. For reference, I now give you the formula for the total momentum and total relativistic angular momentum of a string, which are obtained by integrating the conserved currents, or more precisely the time worldsheet time components of the conserved currents over the worldsheet. Okay, so that completes our discussion of conserved quantities. And so far, we have been doing everything without explicitly solving the equations of motion. But this can, of course, be done. And in the conventions usually used in string theory texts, that is formula 73, which looks a little bit baroque. So maybe I show you before, or we go before we look into this formula, we look into how you would normally do in the mathematics, do this in the mathematics class. So what we normally would say, okay, we have a solution to the wave equation, which I can write as a function of sigma plus plus a function of sigma minus. It must be periodic in sigma 1. So that means it's periodic in sigma plus and sigma minus. So I write down the corresponding Fourier series. Here I've taken out the constant mode and written it separately. And the only point where we need to be a bit careful is that a term linear in sigma 0 is also allowed, because it's linear in sigma 0, so it satisfies the two-dimensional wave equation. And for sigma 0, we don't have any boundary condition to impose. A linear term in sigma 1 would solve the equation of motion, but it would violate our periodic boundary condition. In this form, it's not so clear that, or it's not manifest that this is a function of sigma plus plus a function of sigma minus, but of course you can split up sigma 0 in a term with sigma plus and then a corresponding term proportional to sigma minus with the same coefficient, and then you have formally written it as a function of sigma plus plus a function of sigma minus. Now, but the coefficients will be the same. Now, let's look how the formula is conventionally written in string theory. We will appreciate over time why this somewhat funny looking conventions are taken in string theory. Now I have to find my slide. Oh no, this is not the right spot, so I need to scroll forward. No, sorry, probably too far, sorry. Oops, what happened here? Maybe I need to reload my document. So let's go to this page here. Oh, sorry. Yeah, okay, and now it seems to be sorry, something happened to my document. Maybe I import it again. Seem to have somehow damaged my file, but no worries, I can load it again. Oops, sorry, now my I don't want to update. Sorry for this. It's the first time that I have such an issue with this program. Okay. Okay. Now I should be able to scroll forward to where we left off. Yeah, which is this here. So you now will recognize that this is indeed a formula with the same structure as we had before. So we have here a constant term, we have a term linear in sigma 0, and I write my coefficient in this particular way with the notation p mu, which we will see why I do this. And then here we have these Fourier series which correspond to waves being placed on the string. And again, there is some conventional factors in front and some factors of I, which we will see later why they are convenient, and also 1 over n, which we will also see later why it's convenient. But that's just a conventional way of writing it a bit differently. And we also note that, of course, this has to be real. So x and p are real. And since we use the complex exponential, we have a reality condition which relates alpha n with alpha minus n. And here I've expanded on this remark that you can write the term linear and sigma 0 as a term linear and sigma plus a term linear and sigma minus, but the coefficients need to be the same. So here it corresponds to symmetrically splitting the momentum between the left and the right numbers. Okay, now the coefficient of sigma 0 was called p mu, and that was with hindsight, because if we now compute the total momentum of the string by integrating our Noether current, if you substitute in, well, if you take x here, differentiate it with respect to sigma 0, and then put it into this integral, then you see that this coefficient p mu is indeed the total momentum of the string. We can also compute how the center of mass of the string moves. In this case, we have to integrate x mu over sigma 1 and normalized by the interval. And then, I think here I forgot factor pi over t, we see that gives us a constant term plus a term linear in worldsheet times sigma 0 with the momentum as a coefficient. So this exactly takes the form of the motion of a free relativistic particle. So this shows us that if for a freely moving relativistic string, the center of mass moves like a relativistic particle. And on top of this, we have this left and right moving waves, which are parameterized by the Fourier coefficients alpha. Now we see in several of these expressions that the string tension T always comes packaged up with pi. This suggests that we should use a particular system of units called string units, where in addition to c equals 1 h bar equals to 1, we put the string tension to 1 over pi, and then many formulas look much nicer. In particular, for example, in 76, my pi t becomes 1, and I'm rid of it. We can also express our conserved charges for conformal symmetry using our solution by substituting in the solution into the expression for Lm. I don't do this here explicitly, but you should maybe check. And this gives us infinite sums which are quadratic in the Fourier coefficients. To be precise, x does not enter into these formulas, but the momentum p also enters into these formulas. But I can then introduce the notation alpha 0 with the appropriate coefficient of proportionality, so that I don't have a separate term in these infinite sums. Okay, good. Now let's get something out of the things that we have derived. First observation is the following. Let's compute the canonical Hamiltonian, which is the integral over the string of the Hamiltonian density. And the Hamiltonian density is the Legendre transform of the Lagrangian density, which I've written in here. Oops, written here. And if you do this, you find that the canonical Hamiltonian is precisely L0 plus L0 tilde. And that's why we call L0 plus L0 tilde the worldsheet Hamiltonian. And it is the conserved charge associated with translations of the worldsheet times sigma 0. The other combination, L0 minus L0 tilde, is the conserved charge for translations in the spatial worldsheet coordinate sigma 1, and therefore we will call it the worldsheet momentum. At this point now, we can get some real understanding what the Hamiltonian constraint means. Hamiltonian constraint is that the worldsheet Hamiltonian is equal to 0. Now we can again dig into L0 and L0 tilde and take them apart into the contribution from the momentum and the contribution from the Fourier coefficients, which I've done here, introducing some handy notation for the oscillator part of L0 or the Fourier part of L0, which sometimes are called total occupation number. Now, if you use that in my convention with a minus sign, m squared is minus p squared, then we realize that the Hamiltonian constraint actually gives us a mass formula, which tells us the mass squared of a string is proportional some numerical factor to the string tension, but then it's determined by this total occupation numbers. Completely intuitive result, of course. The total mass of a string, which is its total energy measured in the rest frame, is determined by how much oscillation I have switched on. We have a second constraint, which is L0 minus L0 tilde is equal to 0, or L0 equals L0 tilde, which means n equals n tilde. And that is a balance condition, which tells us that the left and right moving excitations must contribute equally to the mass. Good. Closed strings. Now for reference, I give you also the solution for open strings. With Neumann boundary condition, it takes this form here with the cosine n sigma 1, which tells us that indeed we get standing waves. By the way, if you repeat this with Dirichlet boundary conditions, you will not be too surprised to find the cosine being replaced by a sine, because with Dirichlet boundary conditions, we keep the ends of the string fixed. Whereas for Neumann boundary conditions, the ends are free to move and momentum is conserved at the ends. If we insist, we can still write the solution for an open string as the sum of a function sigma plus and sigma minus, but this time not only the momentum must split symmetrically, but also the Fourier coefficients are the same. And this is again the way how left and right moving waves then organize themselves into standing waves. For reference, the conserved charges of conformal symmetry for an open string can be expressed in terms of the alphas, only one set. It's given here. Again, this also includes the contribution from the momentum. The canonical Hamiltonian is then simply L0 for an open string, and we get a similarly looking mass formula to the closed string with just one set of Fourier modes entering into the mass formula. What is a fun thing to check, which should be very quick for you to do, is that with the Neumann boundary conditions and imposing the constraints, one can show that the ends of an open string always move with the speed of light. I'll leave it to you to check. That's a fun fact that everybody should interested in string field should check once for him or herself. Good. Now to end this part 2, which is our introduction to the relativistic string, I would like to give you a schematic outline how we have to set up the quantum theory. What we'll then do is we will have 2 further parts where we look into conformal field theory and where we will develop the tools which help us to solve certain problems that we encounter when we try to quantize a relativistic string. But let's have a schematic preview. What we decide is we want to commit ourselves to quantizing the theory in such a way that we maintain Lorentz covariance. I will tell you something about non-Lorentz covariant quantization later in the course, but for the time being, we commit to a covariant quantization scheme. Now, what is the usual rule by which we quantize? Well, for a non-relativistic particle, the relation is that in units where h bar equals to 1, the commutator between position and canonical momentum is I times the Kronecker symbol. And here we use that canonical and kinetic momentum are the same unless we put our particle into, say, a background magnetic field, which for the time being we don't do. Now, how does it, by analogy, then have to look like for a relativistic string? Well, I now have to work with the string coordinate x mu, which is a function of sigma 0 and sigma 1. And the canonical momentum, general definition, is variation of Lagrangian with respect to time derivative of x. But in the conformal gauge, it's just proportional 2x dot or d0x. So this is then my pi here. Now, what do we have to make on the dependence on sigma 0? Well, it tells us that we are working in the Heisenberg picture of quantum mechanics where operators depend on time, in our case on worldsheet time. In this case, it is sufficient to just specify the equal time commutators, because for other, for non-coinciding times, the correlation, the commutator is then fixed by the dynamics of the system, by the equations of motion. What do we have to make of the indices? Well, we have now indices mu and nu, and that works like for the non-relativistic particle, except that relativistic covariance forces us to use the Minkowski metric here. And that will cause some complications because the Minkowski metric is indefinite. And finally, we have a dependence on sigma 1. Yeah, this is what labels, so to speak, the points along the string. And this quantity is treated like an additional index, in our case, a continuous index, and therefore the Kronecker symbol is the delta function. Well, more precisely, I have to take into account that I have boundary conditions in sigma 1. So it is a periodic delta function, or Dirac comp, as it is sometimes called. And periodic delta function can simply be characterized by its Fourier series. Now, so you will probably know that the Dirac delta function normally is represented by a Fourier integral. And if you impose periodic boundary conditions, want to have a periodic boundary condition, then it becomes in the state a Fourier series. If we take these, or postulate these commutation relations 91 and substitute in the mode expansion, we get a set of commutation relations for the modes or components. For x and p, we get something which looks similar to what we have for a particle, which we expect since we know that the center of mass moves like a relativistic particle, but it involves eta mu nu, the indefinite space-time metric. And then we have relations between the Fourier coefficients, which look like this. We also have to remember that overall the capital X is real, or as an operator than Hermitian, and that means that X and P are Hermitian operators, whereas for the mode operators, alpha m is related by Hermitian conjugation to alpha minus m. Then comparing this with the commutation relations, we realize that this looks like a harmonic oscillator, and we can make this precise by performing a suitable rescaling, and then we obtain almost, but not quite, harmonic oscillator commutation relations for creation and annihilation operators. The only thing which is different is that Lorentz covariance has forced upon us that we have the Minkowski metric here, and therefore in at least one component we don't have a harmonic oscillator but an inverted harmonic oscillator. And with this minus sign, it is not clear how we can get a Hilbert space out of this, which is positive definite. So here's a schematic view how the covariant quantization program works. The first step is we simply represent the commutation relations that we have found on a space which we call the Fock space. This is done by choosing a ground state or vacuum, which is characterized as follows. I pick half of my Fourier mode operators, let's say those with a positive m, and declare them to annihilation operators, so they map the ground state to 0. And similarly, my ground state should be translation invariant, so it's annihilated by the momentum operator. This defines me a big configuration space, or analog of the configuration space on which I have implemented my commutation relations. But then I have to impose the constraints. You've seen that classically what the constraints do, that they select among the possible configurations a certain subset, which is characterized by Lm and Lm tilde being equal to 0. In the quantum theory, we implement this in the way that we say we select a subspace of physical states out of F, and these physical states are characterized in the way that matrix elements of Lm and Lm tilde between physical states have to vanish. There's some more fine print to this, which we will analyze in detail in coming lectures. But this is not the end of the story, because we have also seen that the conformal gauge is not a complete gauge fixing. And therefore, there are residual gauge symmetries which correspond to conformal transformations. We will see more explicitly in future lectures how conformal transformations act on states and map states to other states. But what we then therefore have to do is, if two physical states are related by such a conformal transformation, then we need to identify them. So this is an additional gauge symmetry that we have to divide out. And this is then how the physical Hilbert space arises. It comes out of the physical subspace by identifying states which are gauge equivalent. This, if it works, should also get rid of the problem that on the original Fock space F, we cannot have a positive definite scalar product, because by Lorentz invariance, all the commutation relations involve this indefinite metric eta mu nu. And the way this works out is that by imposing the constraints, we will get a subspace of physical states where the negative norm states have been eliminated, but a phys will still contain states which have zero norms, so-called null states. And these null states then should correspond to the residual gauge transformations, in the sense that two states in F phys which differ by such a null state are related by a gauge transformation. And then by dividing out all the null states, we should hopefully end up with a Hilbert space which really carries a positive definite scalar product. Now, this is not easy to work out in all details, but we will not see all the details, but we will see the relevant steps, and in particular, we will see and understand why this does not work in an arbitrary dimension, but why this leads to the famous observation that a string theory can only be defined in a certain number of dimensions as a quantum theory. The problem is that otherwise you don't get a Hilbert space with positive definite scalar product, thus enabling the usual probability interpretation of quantum mechanics. Okay, good. I think that is what I wanted to do today, but we have a little bit time left. So let me check whether there is something in the chat, and otherwise, okay. If somebody has an urgent question, you can, or a question, you can type it in now. Otherwise, I can give you a sneak preview already into the next part of the lectures, the one on conformal field theory. So I don't really see something coming up here. So let me load the next set of notes, part 3. And yeah, and by the way, I'm of course always relying on your feedback about my pacing. No? I think that is about the normal speed of lectures which has usually worked. But if I'm going too slow or too fast, then you need to let me know, because otherwise I can't act on it. So what is now the idea in the next part of the lectures? We will elaborate on the observation that string theory based on the Polyakov action in the conformal gauge is a conformal field theory. And therefore, we now decide to study conformal field theory in a bit more detail. And we will go over conformal field theory twice, in once, so to speak, in a bottom-up and then in a top-down approach. And the bottom-up approach, we will take a particular example, namely a massless scalar field in 2 dimensions, to kind of discover what conformal symmetry does for us. And of course, a massless scalar with an action as given here in formula number 1 is the same as one string coordinate if it is understood that we are in the conformal gauge. So in a sense, we are doing string theory with a one-dimensional target space. And that getting rid of the Lorentz index gives us some simplification, and we can focus on what conformal symmetry does for us. Since Litecoin gauge is extremely convenient, I've also for reference written down how this action, which is a Poincary action evaluated in the conformal gauge, looks like in Litecoin coordinates. And for reference, I have brought back the equation of motion. And now let's look at the worldsheet. So if we consider closed strings for definiteness, then the worldsheet will be a cylinder. Period. Now, one element that we will bring in order to formulate conformal field theory is the Euclidean formulation of the theory, which means that we are now making a so-called Wick rotation, which replaces the worldsheet time by minus I times the worldsheet time. As you can see in formulas 3 and 4, what this does for the Litecoin coordinates. And what I then do is I see that I can combine Litecoin coordinates into a complex coordinate W, and this is a complex coordinate on the Wick rotated cylinder that I have. So that is the first step. I have a theory in Lorentz signature on a cylinder. I make a Wick rotation. I have a theory on a Euclidean cylinder with a coordinate W. And then I do some further step, namely I make a conformal map from this Wick rotated cylinder to the complex plane. And this conformal map is simply given by the exponential function. And this gives me then a complex coordinate z, and its complex conjugate z bar on this complex plane. And these will be the basic variables with which I will work in my conformal field theory setup. Let me show some picture about this. Okay, here we go. So what you can see here in black is the worldsheet cylinder with coordinates sigma 0 and sigma 1. Good, if I do the Wick rotation, then sigma 0 becomes imaginary. But let's focus here on how time evolution is described in the two formalisms. So in normal formalism, where sigma 0 is the worldsheet time coordinate, time flows along this cylinder. If this is mapped to the complex plane with the coordinate z, then the infinite past is mapped to the origin of the complex plane, whereas the infinite future of the cylinder is mapped to the infinitely far point on the complex plane. And that means that we have here a correspondence where time is represented in the complex plane as a radius. Or if I read it as evolution of a string along the cylinder, then in the plane, this closed string originates at the origin and then moves out as a circle out to infinity. No, I think I don't need this today. So just in the last 2 minutes, let's go back to slides and give you some reference here. So here's a little dictionary how quantities that we are familiar with and things that we are familiar with relate from the cylinder to the complex plane. And as you can see here, in particular, the Litecoin coordinates come in very conveniently. So we have seen time becomes radius, and therefore time translations along the cylinders become dilatations or scale transformations in the complex plane. Time ordering becomes radial ordering. Spatial translations become rotations in the complex plane. And if you go through derivatives and tensor components, and the Litecoin derivatives become the so-called Wirtinger or partial holomorphic derivatives, which are complex linear combinations of x and y, where x and y are the real and imaginary part of z. And if you use this to rewrite tensor components, then Litecoin components of tensors, as an example here, the energy momentum tensor, become holomorphic or anti-holomorphic coordinates, which are labeled by Z and Z bar. Okay, good. There's another slide for reference, but my alarm has gone off and it tells me that I've now talked for 50 minutes, which is probably enough. So let me stop sharing and go back to the speaker view. And are there any immediate questions? You can also, of course, post things in the forum or email me or contact me in any other way. Let's check whether there's also nothing in the chat this time. So I hope everybody is okay and enjoying and following the lectures. Please do really have a look at this problem sheet or example sheets that I've posted. It's really important to be actively involved with the lectures. And if any questions come up while you try to do these problems, or if you then discover in your study of the notes that something is not perfectly understood, then please, by all means, let me know in one way or another. Otherwise, from my point of view, from my point of view, this is all I wanted to say. If there's no questions, then thank you again for joining. Hope you have a good week, and I'm looking forward to meeting you again next week, same time. I'll stay online as long as everybody has logged out. So goodbye for now. Take care. Stay healthy.